So I'll be presenting the NFDI4Biodiversity knowledge graph with the use case for trait data. So this is a work I carried out with my colleague Jan Phyllis and also colleagues from the NFDI4Biodiversity, Henry and Bernard from Uni Marburg, and Tarek and Brigitta from Uni Jena. So I will start by saying what are knowledge graphs. So this is a definition from Wikipedia. Knowledge graph is a knowledge base that uses a graph structured model to represent data. So for instance, here you can see a knowledge graph about observations. So an observation has a measurement. Measurement has a unit, for instance, here micromoles per liter. And it's a measurement of the characteristic nectar sugar concentration, and it has a value 0.75. So additionally to the knowledge, there is also the encoding of the semantic of the relationships of the graph. And this is done by describing the classes, basically in an ontology. For instance, saying what the entities are. For instance, here, this is a measurement and all the definition of the relationships between the different concepts or classes. So for the NFDI4Biodiversity knowledge graph, what do we have? So basically, we have a collection of data silos that are not interconnected. For instance, data providers, repositories, or collections. So, and also a set of terminologies, taxonomies, and so on. So those are not interconnected, which limits their full potential in broader context. So our aim is to bring this in a knowledge graph, so transform basically the data into linked, unified, and actionable knowledge. So the users don't have to go to the different repositories. Instead, they can just access the knowledge graph and have all the interconnected data in one place. So what do we need for that? So we need some ingestion pipeline to transform the data into RDF, basically. And more importantly, we need to do some knowledge representation, basically to define a semantic data model, which will capture the meaning and the context of the data. And also, as I mentioned, describe the relationships, attributes, and so on in a semantic model. So for that, so we can reuse existing terminologies or develop own terminologies, and we have them in our terminology service, BioDiv portal. So for instance, until now we have 55 ontologies in the portal and up to 3 million classes already. So I will also talk about how we use this knowledge graph for instance, for visualization, for question answering, semantic search, and also recommendation. So basically applications that access the knowledge graph that the users can use. So I will start by concentrating on the knowledge representation and specifically for trait data. So there is a standard that have been developed by our colleagues from Uni Jena and from BGBM, for instance, which is called the Ecological Trait Data Standard. So it's a vocabulary providing essential terms and for describing data sets of functional trait measurement and facts for ecological research. And if we can, we have a look at typically how trait data look like. Basically, it's a matrix of species and traits measurements. For instance, here we can see the species here have been, there was a measurement of body length, body weight, height, and thorax length. So basically, several trait measures per species. And what is required is first to transform this table into a core observation table, which means to transform the columns into rows. So one row per measurement. So you can see here, for instance, body height is now in a line with its name and trait value. So basically, we will have for each line from the original table 4 new lines with the trait name and trait value. And then, so we have, this is the minimum requirements from the standard, which is to have a trait value, and for numerical values, trait units. Then have a trait name that is linked to a standard definition, which means a concept from an ontology, and to have a scientific name that is also obtained from an ontology or taxonomy. So you can see here in the example, for instance, we need to assign original names and unambiguous URIs to standardize basically the content of the table. For instance, here we have species URIs from GBIF that are already in the table, and we could also connect, for example, the trait names to the observations attributes, the ontology, sorry, the biological attributes ontology. We could have standard names for trait units from the quantity and units ontology, and we could have, for instance, for basis record, URIs from the GFBio record basis ontology. So once we have connected all the content of the table to URIs or concept basically from ontologies that come from BioDiff portal, we can transform the data into a knowledge graph. So the ecological traits data standard is one of the ontologies in BioDiff portal. And you can see here all the metadata information about the ontology itself. You can download it. You can see the link to the documentation, to the GitHub repository, as well as the reference paper. This ontology has is basically kind of a schema, so it has more properties than classes. It has 129 properties, and if you go to the properties tab, here you can see them. For instance, here I show the trait ID property, which has a description that it should be a unique identifier for a trait. And also you can see here some examples, like trait that can come from the top thesaurus or the trait ontology, the Floppo ontology, and so on. And you can also the information that this is a recommended property and it's organized in the class trait data. So now that we have our knowledge representation, basically all the ontologies, we can transform the original data that are either in tabular form or from databases into RDF. And I will show how we do it for trait data from the TRI database from Pangea. with the help of LLMs. So this is the ingestion pipeline for for the knowledge graph population. So the first step is to transpose the table. For instance, here you can see in the example we have the attributes that are in the columns, so the traits, body height, weight, and so on. So what we need is to have a core observation table with 1 row per measurement. So what we use for that is the AutoText Refine tool that transposes basically the columns into lines, and the values would be here per line. So once we have the core observation table with 1 row per measurement, we can standardize this. So basically adding a column to the core table with the IDs instead of only having the names. For instance, here in the example, there are the GBIF IDs for the species. And we could also have use the biodiff portal annotator to for the trait names, for instance, to have URIs from ontologies. For instance, here for the body height, body weight, body length traits, we could use the URIs from the OBA. So once we have these tables with URIs, we can do the mapping into RDF. So we have here an example for our example, we or basically for any table that is of a structure of the ecological trait standard, we created a mapping that is R2ML mapping. That is a mapping language for transforming RDB or tabular data to RDF. And we can generate basically the RDF graph from the table. For instance, here you can see the observation 25 with the taxon ID for this species, and additional attributes, for instance, which traits have been measured, the trait value, and so on. So I will show now how we do we use basically the pipeline for data that come from the plant trait database. So this data basically is already transposed. So we already have 1 observation per line, and also the trait IDs have been standardized using the top thesaurus. So what we did additionally is connect the species names to the catalog of life IDs, and the unit names to QUDT. And then we can basically, based on the table with the IDs, transform the tables into RDF. And you can see here, for instance, the generated knowledge graph with in blue the species, and in red the trait data. So that are connected with has identified taxon. You can see also what traits have been measured. So we concentrated on the plant height, vegetative traits in this data set. And so you see all the connections, and you see all the trait data that are that pertain to a specific taxon. And additionally, there are also some metadata about the data sets. So now I show how we we use the ingestion pipeline for Pangea data. So basically, Pangea data is a typical structure for trade data, which means that the columns, like the trades, are in column names. For instance, here for number of leaves, height, and so on. So there is a lot of work from curators to basically standardize those names. For instance, here you can see SLA, which have been curated to be the specific leaf area, and also giving the units that have been used. So what we are working on is to help this process with large language models, and basically try to generate from the original names, like standard names. For instance, here you can see the SLA, which have been detected as specific leaf area, or TAA, for instance, as total amino acid concentration, and so on. This have been already done by OpenAI GPT 3.5 Turbo without context. And if we use GPT-4 with context, it's even better results. Like, for instance, you can see additionally, there is also the standardizations of the names of the units. For instance, here micromoles per liter have been detected here as well, square centimeter per gram, and so on. So once we standardized those columns names, for instance, here leaf area, we annotate them with ontologies from BioDiff portal. For instance, leaf area is defined in FLOPO, leaf dry mass in the top thesaurus, and specific leaf area in the environmental thesaurus. So we are using all the URIs coming from the ontologies, and then we can apply the transformation model to generate the knowledge graph. You can see here, for instance, that we have additional traits that have been measured, which, for instance, leaf dry mass, or number of leaves, plant height, vegetative, and so on. So here we can see the same species that have been also measured in the TRI database. So we basically can connect observations from different sources in one graph. So we also integrated data, the RDF data that comes from additional sources. For instance, our colleagues from University of Vienna also worked on generation of a knowledge graph based this time on the SOSA ontology, which also describes observations and connect them to feature of interest, properties, and as well as procedures and sensors. And here an example of or an excerpt from the generated knowledge graph. And you can see, for instance, here data that comes from Naturgucker data sets, which are occurrences of species. And we have here again the same species, which is red clover. And you can see that additionally to the IDs from GBIF, there is also the connection to the red lists. and as well as the wiki data identifier, which enables us to have additional information and even, for instance, here the picture of the species. Okay, so now I will go on and show what we are working on for the both the visualization and the question answering. So for the visualization, we are working with our colleagues from Uni Marburg with the FAT tool for the visualization of observations or data on a map. And the addition, if we have the information from the knowledge graph, would be to be able to have facets about, for instance, the species or the traits that we would like to concentrate on. And for example, here I took the plant trait vegetative for this specific tree. And you can, for instance, have a histogram of the height of this species over time. That is what is planned for the analysis and visualization. Then we are working on question answering system that is an agent-based framework. For instance, a user can query with a question the knowledge graphs, and we will send. So we have a multi-agent system that with multiple agents. One agent will translate the question into a Sparkle query. A second agent will validate the query, give it back to extract the data, and we send the data to a third agent which will create an answer in natural language that will be returned to the user. So an example, I show here even an example that is in German, which asking for observations for specific species in Germany. And the first agents generated the Sparkle query to concentrate on this specific family of species. And the second agent basically answers, like the third agent, sorry, the one for the question answering will transform basically the results into a natural language answer. So it's saying that the observations of this family have been found in those regions in Germany, and also additionally, it's also said who were the authors of those studies. Okay, so I will finish by saying what we are planning in the future. First, we would like to work on the scalability based on user requirements. There are multiple solutions for that, which are either aggregation of the knowledge graph content. Because the transformations generate a huge amount of data, so the idea would be maybe to concentrate on aggregating this information to be able to answer questions, specific questions. The second solution would be dedicated to triple stores per types of data, and with a federation of those triple stores. And the third solution would be virtualization with databases. We also plan to strengthen our collaboration with the basic service knowledge graphs for NFDI. KGI for NFDI. So basically to support the infrastructure deployments, so we can ensure stable and scalable implementation. And we would like also to ensure interoperability across disciplines and other NFDI consortium.